Welcome back everyone. We're gonna do part 2 for this video lesson. We're gonna talk about how to do calculations using Hooke's Law in this video's lesson. Now before we talk about Hooke's Law, let's recap back what is this topic is all about. This topic is all about how elastic objects deform or how elastic objects change their shape. So here I have a spring, 2 springs in fact, I'll only be using one. If I put a force or a weight onto the spring, it will deform or it will change its shape or size. In this case, the spring will, wait, let me just stop the spring. The spring will extend. Okay, so before, let me put on this line here. Okay, so before that's the original length of the spring here. And then when I put on a mass or a weight, the spring will then extend to a certain amount. Okay, and we also looked at Hooke's law. What is Hooke's law? Hooke's law is basically the force that you give to a spring is directly proportional to its extension. That means if you double the force, the extension will also double. So let's double the amount of force we give here. Now we have 50. Now let's put on double that. So double of 50 is 100. And you will see, let's stop the bouncing. You see the extension is also double. Let's say let's use a much heavier one here. This is 5 times as heavy than the original one. So if this is 5 times as heavy or 5 times the force, then the extension will be 5 times as longer. So that is Hooke's law. We can also use Hooke's law to calculate forces and extension of elastic objects. And this formula is F is equal to K times E. Now F means force, E means extension, and K is something that's called spring constant, and we're going to talk about that now. So what is spring constant with the symbol small k? It has a unit of Newton per centimeters. So spring constant tells us how hard it is for the spring to be pulled. So some springs are harder to press and pull than others. Spring constants tell us which springs are hard and which springs are soft. A spring with a large spring constant means that it is difficult to stretch, while a spring with a small spring constant means that it is easy to stretch. So let's look at this example again. I have 2 springs. I can change the spring constant, of course. The first spring here has a small spring constant, and the second spring here has a large spring constant. Okay, let's put on a weight of 100 grams to this first spring. Okay, let's stop the bouncingness. That's the original length. Let's put on a ruler to see how long it has extended. And let's put on a movable line here. So in the case of this first spring, when you give a mass of 100 grams, it extends by 22 centimeters, okay, just from this diagram here. What about the second spring? The second spring has a larger spring constant. Let's put on 100 grams, the same mass. And you will see it doesn't extend that much. So the other one is shorter. It doesn't extend as much. So what does this mean? The second spring has a larger spring constant, as you can see. Because it has a larger spring constant, that means it's a harder spring to pull. If you give the same mass, it doesn't extend as much. The spring here has a smaller spring constant, so it's easier to pull. So spring constant tells us how much force is needed to extend the object by a certain amount. In this case, it's usually by 1 centimeters. A spring with a spring constant of 100 newtons per centimeter needs 100 newton to extend it by 1 cm. Sometimes the spring constant is called the force constant. So let's do an example question here and see how we can use the Hooke's law formula to calculate an extension or to calculate force on a string. So the question reads, a stretching force of 50 Newton, so this is F for force on a spring, produces an extension of 5 cm, so that's E for extension. Find K, the spring constant of the spring. So in order to do this, you need to use the formula F is equal to KE. F is 50, K we do not know, let's leave it like that, times extension is 5 cm. Okay, and then you make K the subject of the formula. So in order to solve K, you have to move 5 to the other side. It's multiply, so if you move it to the other side, it becomes divide. So 50 divided by 5. So 50 divided by 5, that is 10. So therefore, K is equal to 10 newtons per cm. And that's the answer for the first one. So B, with the same spring, find the extension produced if a force of 30 newtons is applied. So it's the same spring. That means we can use the same spring constant. So here's the formula again. And this time, you want to find the extension. This time, the force is 30 Newton. So it has changed now. K, we already find how much that is. That is 10 Newtons per centimeter. And this time, we want to find E. So in order to find E, we move the 10 to the other side. Now, because this is multiply, it becomes divide if you move it to the other side. So it's 30 divided by 10 is equal to E. Therefore, 30 divided by 10, that's 3. So therefore, E is equal to 3 cm. So it has extend by 3 cm. C, the force required to stretch the spring by 7 cm. Now we want to find force for E. So we use the same formula again. This time we want to find a force. So F is the value we do not know. K is 10. This is what we found out here just now. Times the extension. The extension is 7 cm. So 10 times 7, that is 70 Newton. And that is the answer. To summarize this video lesson, remember what is spring constant. If a spring has a large spring constant, that means that spring is a hard spring. If the spring has a small spring constant, that means it is a soft spring. That means it's easy to pull. And make sure you remember F equal to KE. That's the formula that we use for elastic objects. Next week, we're going to move on to part 3 and we're going to look at extension load graphs.